Hey guys, welcome back to this lecture series on control engineering, and so today we will keep continuing with the state space analysis. So far what we have seen is given a system, how to write it down in the state space form. Given a nonlinear system, how would you linearize that around an equilibrium point and analyze stability. So today we will do further or go a little further deep into this topic and essentially deal with what is called as controllability. And what does controllability mean? Is a system always controllable? What if it is not always controllable? And if it is controllable, how do we control it? So far we have seen control methods or design methods using the root locus, where we take the help of a root locus plot to achieve the desired closed loop specification. Similarly, we did some design problems with the help of Bode plots. So, let us see what all that means in the context of state space analysis. Okay, so let us quickly write down what have we seen so far. So far we have had state space representations, and what we saw, yes, in the other lectures was three different forms. So, one was the controllable canonical form. Similarly, we had the observable form and also the diagonal form. And we also saw how to convert a given system into its diagonal form. There are several other details of the diagonal form in the terms of the Jordan form, but we will try to skip that. Okay, the first is now how to convert a system from a controllable to observable, or observable to a diagonal, or whatever. So, if I say I have a transfer function and I convert it into a state space. Now, is this state space representation unique, and how are these three related to each other? So, let us do it in a little abstract way. Let us say, or whenever I am converting, so let us say I have a system which is like x dot is Ax plus Bu, and I say how do I convert it from one form to the other? And we had earlier seen that we could actually do a transformation of A matrix to something which looks like P inverse AP. Okay, so where does this come from? So, let us say I start with x, I define a new variable z and say x is related to z via this matrix P. Okay, so this matrix P is invertible. So, P is okay. So, what happens now? So, if I write down this in terms of the z coordinates, I will have z is P inverse times x, which means that z dot is P inverse of x dot. This is P inverse of x dot. What is x dot? X dot is A x plus Bu, and what is x? X is now P inverse z. So, I have, if I write it down again, so x in terms of z would be P inverse AP times z plus P inverse B times U. So, I have a system in the new coordinates z which looks like, let me call this say A tilde times z plus B tilde times U, where this guy P inverse AP is the A tilde and P inverse B is the B tilde. Okay, so the invertibility is needed because, well, we need the matrix to be invertible here, and you can always go back from the x to z and z to x and vice versa all the time. Okay, so so given a system in a certain way, say it's in the observable form, I could go to the controllable form via some transformation P. Okay, what is this transformation is what we will see a little later, which kind of P to use to get from a standard form to a controllable form, standard form to an observable form, and so on, right. Okay, now what has changed here? Now, can I say that the system in the x coordinates is the same as the one in the z coordinates? Well, let us see. So, what we are interested typically is in the pole locations. Okay. So, we will compare the characteristic equation of this guy to the characteristic equation in Z, characteristic equation of the system written down in the x coordinates to the characteristic equation of the system written down in the z coordinates. Okay. So, let us see. So, if I write down the characteristic equation for the system in the z coordinates, I will have lambda I minus P inverse A P. So, this will be I can write this down as lambda times P inverse P inverse A P, and just multiplying by P and its inverse. So, this will be P inverse lambda I minus A, where I is the identity matrix, times P, and just using some basic properties of matrix, the determinants just come out like this, lambda I minus A times P. So, what am I left with? So, this guy cancels with this guy, and I am just left with lambda I minus A. So, if I equate this to 0, I get the poles. So, which means that if I write this down in summary, lambda I minus P inverse A P is lambda I minus A is 0. So, the characteristic equations are the same, which means that the poles here and the poles here would exactly be the same. So, almost like nothing changes, right. So, I am exactly dealing with the same system, I am just doing a little bit of coordinate transformations, and we all would have done coordinate transformation in some math course, vector calculus, where we transform from a rectangular to a polar coordinate, cylindrical coordinates, and nothing changes in the system. Something very similar is happening here, right. So, each of these forms, the controllable, observable and diagonal, are useful in their own way. A bit of the analysis which we will do as we progress through this lecture. Okay. So, the next thing is controllability. So, let us again look at it with the help of an example. Okay. So, let us say I am moving in a plane. Just for simplicity, right? This is just for illustration, and say I have a simplified model of a car, and say all I could do is I can just control, or I can just move in this direction, right. I can just go forward, I can go back, but steering is not allowed. So, this movement is not allowed. Okay. Now, with the application of input u in this direction, I can move forward, right, in this way. Application of u here, I can move backwards. Now, can I say that this simplified version of a car, okay, the picture is not drawn very well, but can we say that this is actually controllable? Right, but I am just allowed to move this way or this way. So, if you look at it from a normal car objective, whenever we drive a car, what would we want is we want to drive across the entire domain, right. We want to go this way, we want to go this way and so on, right. So, if I so what should also be allowed is that I start from that position and I end up here, okay. But this control action u will not allow me to go to this position, essentially because the steering is not allowed. Okay. Now, how do we qualitatively analyze this, or when is a system controllable? The system here with just the two u's, which either goes in this direction of x2 positive direction or in the negative direction of x2, is this controllable? Or for complete controllability, I also need the steering, right, so that I can go from this position to actually this position. Okay. So, let us first understand this with the help of an example, right. So, I have a system, well, in the very beautifully written down in the diagonal form, x1 dot is minus x1 plus u, x2 dot is minus x2 plus u. Okay. So, these are essentially differential equations. If I just try to solve those, I get something like this, that x of t starting from initial conditions, we will have a solution like this, which essentially means I will ask myself a question: given initial states x1 naught and x2 naught, what are the states x1 and x2 I can reach after time t. Okay. So, if I again were to draw a graph of this. So, let us say I am moving again in R2, say x1 and say x2, okay, and say I am starting for simplicity, say I am starting from the origin, right. So, I have a system in R2 again of the form x dot is Ax plus Bu. Now, I would ask myself a question: with any given u, which is arbitrary, unconstrained, but bounded, what are the directions can I move? So, let us say I can move this direction, this direction, this direction, this direction, all 360 degrees, right. So, this would mean that starting from origin I can reach any other point in the x1 x2 plane. So, if I ask a question, what are the points one can reach starting from the origin? With application of appropriate control. If I say that I can reach all of this space in the plane, any point, then I can say that I can reach entire of R2, or the reachable subspace is R2, the entire x1 x2 plane on both directions. Okay. Similarly, I can also say, well, starting from any other points, or say what are the set of initial conditions that can steer the system to the origin. So, if I say if I start from here, so this is my x1 x2 plane, by the application of some control can I go back to the origin, starting from here can I go back, right. And then if I find the set of all points, that will give me the controllable subspace. Okay, well, what is holistic about this origin? Nothing really. I can even say what are the set of initial conditions which I can reach this point or this point. There is nothing really holistic about this, or even this origin here. So, the first thing, reachability will tell me what are the points I can reach starting from a given point, which in this case is the origin. Controllability would mean what are the points or what are the initial conditions that will steer me to the origin by application of proper control input. So, in the linear time invariant case, it turns out that these two are similar, they are exactly the same, that reachability would mean controllability and vice versa. If I could go from this point to this point, I could actually come back from this point back to the origin. Okay. So, if I go back to the example here, if I say, well, if I am not allowing the steering position, the only directions I can move are this one, right. I can move in x2 direction on both ways, but I cannot move in the x1 direction. So, this movement is not allowed, or it is not possible, because I cannot steer, I cannot turn it this way or even this way. Okay. So, let us see more mathematically what these things mean. So, if I say that a system like this starting from any arbitrary initial conditions, what are the points it can reach in time t? Well, if I also additionally impose the condition that, well, I just want to reach the origin like I did here, right. In this example here, my control problem was to find out the set of points, the set of points which will steer me to the origin. So, let us say here that x of t is actually the origin. Okay, so, what will happen? So, I have a 0 here, e power minus t x1 naught x2 naught and this entire guy. So, it turns out if I just rearrange these terms properly, that the set of initial conditions x naught is a set which looks like this, minus alpha t 1 comma 1. What is alpha? Alpha is this thing. Okay. So, in this thing what is unknown? I know the initial condition x1 naught x2 naught, I know the final condition which is the origin, I can compute these guys, only unknown is the input. So, does there exist an input, right, which can steer the states to the origin, or what are the states if I just plot this down in on a piece of paper. So, it looks like this, right. The points which can take me to the origin are only in the green line. For example, if I start at a point say in the 4th quadrant or the 2nd quadrant or any other point which is outside this green line, I will not be able to reach the origin. Okay. Now, let us see some other example, or in this example the controllable subspace is of dimension 1. So, I guess cannot travel all points in the state space. This is something similar to what was happening here, right. I was not allowing steering of the wheels, so I can only move in the positive or negative x2 directions. Okay. So, okay, let us see some other example. I just have again the system in the diagonal form with entries minus 1, minus 2, control as 1 and 2 times u. Okay. Now, if I just write down again the solution of this given certain initial conditions that I want to go to the origin, the equation would transform to something like this. And if I plot what is the controllable subspace or what are the points starting which I can reach the origin, it turns out to be the entire subspace. So, I can start any point in the 1st quadrant, 2nd, 3rd or 4th, all will steer me to the origin or steer the system to the origin, right. So, any point in R2 can be steered to the origin. Okay. So, this leads us nicely to define the concept of controllability. Now, given any system, would I keep computing these solutions all the time? Right. If I have a system which is of dimension 5, it may really be difficult for me to compute all the solutions, right. So, what we will see is given the properties of system, which is x dot is Ax plus Bu, the properties of the system are the A matrix and the B matrix. So, given this information on the A matrix and the B matrix, can I say if the system is controllable or not? Okay. So, what is the definition of controllability first? So, based on what we have argued so far, a system is said to be controllable at t naught, right, if it is possible to transfer the system from any initial state x t naught to any initial state in finite amount of time. So, the key here is I should be able to reach from point A to point B in some finite amount of time. Does not really help me much if I can say that I could travel from Bombay to Delhi in like an infinite amount of time, right. So, you want to travel, or your car should be designed in such a way that you travel in finite amount of time. Okay. So, before I solve any control problem, it is important for me to check if the system is controllable or not. Okay. So, let us see how we do that. So, I am given a system in the state space form x dot is Ax plus Bu, y is Cx plus du. Okay. So, it will turn out that I will just shortly derive this result quickly, that the system is controllable only if this matrix B A B A n minus 1 B, it will be of dimension n cross n times m. If this rank is n, then the system is controllable. Right, and this is both a necessary and sufficient condition. Okay. So, how do we derive this? We will quickly do this. We will not really try to memorize the derivation, but we will try to make use of this relation, the rank condition for controllability. Okay. So, So, I start with this equation x dot is a x plus b u, the outputs really do not matter to us at the moment. So, we can just forget about this for a moment. So, x dot is a x plus b u, the solution would look something like this. So, by now you also know how to compute e power a t. Okay. So, given any initial condition, assume that I want to reach the origin in some time t1, I will ask when does the solution exist. What does it mean by the solution? Again, if I look at this expression, I know the initial condition x naught, I know the final condition t naught, I just want to find out, I also know the matrix A, I also know the matrix B. All I want to find out is, can I reach the origin starting from any arbitrary initial condition by application of some control. So, this is the unknown. Okay. So, we will just use some properties of how to compute the e power a t. You can refer to the earlier lectures which we had on this. So, e power a t can be written as some series in powers of a in this way. Okay. So, what I do is I just plug this in over here. Again, in this expression I am just finding out if there exists a u. The only unknown in this equation is the u. So, if I substitute for e power minus a t over here, what I end up is an equation which looks like this: x naught is summation of this a summation term in the powers of a times some numbers beta k. What is this beta k? So, whatever is in the integral here, alpha k tau, u tau, I just call them beta k. I can always compute this, right. This is always some number. Okay. So, it will turn out that if I I can also write this as x naught is b times beta naught. If I just take for k equal to 0, what I will have is a power 0, which is the identity. So, it will be b times beta naught here. For k equal to 1, I will have a power 1 b times beta 1, this is a b times beta 1 and so on, okay, until I reach n minus 1. Okay. Now, where does the unknown sit in here? The unknown sits in here in this betas, right. The u's appear in beta. So, when does a solution exist? A solution will exist if and only if this matrix is invertible, right. B a b a n minus 1 b is invertible. Okay. So, this is exactly the rank condition which we are trying to derive here, that the system is controllable if and only if this matrix is invertible, not invertible, if this matrix is of rank n. Okay. Similarly, not about the invertibility, but this matrix should be of rank n. Okay. So, this is the condition which we will use. We may not necessarily remember this proof all the time, but what is important is to remember the condition that the rank of this matrix should be n. Okay. So, once I know that the system is controllable, what do I do with it? How do I then control the system? Okay. So, when I was doing the design with the root locus or with the Bode plot, I always knew that, well, I can use either a lead compensator, a lag compensator, or even more simply the gain adjustment. If the gain adjustment does not work, then I go to one of these lead or lag compensators depending upon the specifications of the problem. So, how does that translate in this case? Okay. So, let us come to a problem now. Let us say that for a given system which is of this form, x dot is 0, 1, minus 6, minus 5, can we design a controller u, which I call as a state feedback controller, which has the following specifications, that the damping coefficient is 0.707 and the peak response time is under 3.14 seconds. Okay. So, there are a couple of methods which we could use in this. So, let us just try to write down what the problem statement is for us. So, first is the peak time is given to us, the Tp, peak time should be less than 3.14 or pi. Okay. And it is also said that the zeta, the damping coefficient, should be 0.707. 0.707. Okay. So, now based on this I need to compute what is omega d and what is omega n. So, if we remember the formulas for the peak time, so I think Tp was pi over omega d, and this turns out that omega d is 1 and omega d was related to omega n via the damping coefficient with this formula 1 minus zeta square, which will give us that omega n is 1.414. Okay. Now, what does this mean, right? So, first is, well, it says design a state feedback controller. So, a state feedback controller typically is of the form u equal to minus k times x, okay. Or in this case, since the system is of dimension 2, I will have a k1, k2, x1 and x2, okay. Now, what is the original system? Original system is of the form x dot is 0, 1, minus 6, minus 5x plus 0, 1 times u, okay. So, I could just quickly check what would be the zeta and omega n for the open loop system, right. When u equal to 0, I just would say check it with the help of this characteristic equation S I minus a equal to 0, right. And it is easy to check that the open loop specifications are much further away from what is a desired closed loop specification, and therefore, we need this control. Okay. So, first exercise which you could do is to check if the system is controllable. This means just quickly find the rank of B and AB, and this should definitely be equal to 2, and you can easily find out that the system is controllable. Also, it is easier to check because it is exactly in the controllable canonical form. Okay. So, let us try solving this problem, right. So, what happens? So, if I have a u of this form, my closed loop system looks like this 0, 1, minus 6, minus 5 times x1, x2 plus 0, 1 and u is minus kx. So, this thing here will be minus k1, k2, x1 and x2, which will look something like this 0, 1, minus 6, minus k1, minus 5 here, minus k2 times x1, x2. Okay. So, now the closed loop characteristic equation should be such that these poles or the eigenvalues should satisfy this condition. Okay. Now, when does a second order system satisfy this condition, right? So, how should, which means, okay, this is what is desired in the closed loop case. Okay. So, how does S square plus 2 zeta omega n plus omega n square look like? So, based on these two specifications of omega m being 1.4, zeta being 0.7, this should look something like this: S square plus 2s plus 2 is 0. Okay. Exactly, I am just putting in the values of zeta and omega n as desired. Okay. Now, this is the desired closed loop characteristic equation, which will ensure that the closed loop has a peak time of 3.14 or less, and a zeta, the damping coefficient of 0.707. Now, what would I do? If this is desired, now I compute this guy S I minus this A plus B k, as I would call it. Okay, where does this come from? If I just say in a standard system x dot equal to A x plus B u with u equal to minus k x, I can rewrite this as x dot is A x minus B k x. So, the characteristic equation of the closed loop system would look like this. So, I would compare this S I minus A plus B k with this guy. Okay. So, now I have a equation with two unknowns. Okay. So, let us quickly write down what is the characteristic equation. S square plus 5 plus k 2 times S plus 6 plus k 1 is 0. So, I have to solve for k 1 and k 2. How should this look like? Well, this should exactly look like this. Okay. So, this equation, this characteristic equation should be equal to this characteristic equation, right. So, therefore, I can just compare the coefficients, right, which is 2 is 5 plus k 2 and 2 is 6 plus k 1, which means k 2 is minus 3 and k 1 is minus 4. Okay. That is a simple. So, how do we do this? Take or just check what are the closed loop specifications. Okay. This will translate to an appropriate characteristic equation of the closed loop. This is the desired one. On the right hand side, I need to find out what are the gains k 1 and k 2 that will achieve this desired characteristic equation here. Okay. And then I just write this down, I compare the characteristic equation on the right to the desired characteristic equation on the left, I just equate the coefficients. Okay. So, in some problems it also, the problem specifications could also be not in terms of zeta and omega n, but directly in terms of the desired closed loop poles. Okay. So, if you say that given a system x dot is A x plus B u, this could be x is say in some R n. Okay. Now, the problem could be of find a control law, again u equal to minus k x, which places the closed loop poles at say some values mu 1 till mu n. So, earlier we had the specification in terms of some system performances, a peak time, it could also be in the terms of the settling time or the rise time, damping coefficient and several other things. So, here I just have specifications directly in terms of where the poles of the closed loop system be. Okay. So, in this case what I will do? Well, what is the desired characteristic equation? The desired characteristic equation would be, I just look at this S minus mu 1, S minus mu 2, S minus mu n is 0. Okay. This is, I know all these numbers, right, I know all the mu 1. So, I have a polynomial in s power n with all the coefficients which are known to me. On the right hand side, I would have unknowns in the terms of k 1 till k n. So, I just equate the characteristic equation on this one, which is in powers of s n plus, we will see how to write this, and on the right hand side I should just equate this to the characteristic equation which I get by S I minus A plus B k. Okay. Let us write this down a little more formally now. Okay. So, this is essentially what? So, I have the desired poles which are mu 1 till mu n, and I will have the characteristic equation as a polynomial in S of power n, On the right hand side I know S, I know A, I know B, I just need to find out K. So, I will have again a polynomial here of power n, I just equate these two as I did earlier. Okay. So, well, this is straightforward, right. So, this is exactly what we did here. So, I will just quickly look at this. So, pole placement. So, this procedure which we derived or where we designed the controller, a state feedback controller u equal to minus kx to achieve certain performance specifications is called the pole placement technique. Okay. So, this is required to have the system desired behavior. A necessary and sufficient condition is that the system should be completely controllable. Okay. So, what do I do? Well, I know this mu 1 till mu n, okay, and I just equate these two. I compare the coefficients and I arrive at the desired control law. There is also other method from the controllable canonical form. Okay, let us first write down and then see what it means. Okay, so let us say I have the system in the controller canonical form. Okay, I am just being a little lazy to write. So, let us, for the purpose of derivation, let us just say that x is in R3. Okay. So, if in R3 my A matrix would look like this, it will be 0, 1, 0, 0, 0, 1, and I will have coefficients here minus A3, minus A2, minus A1. The B matrix will have entries 0, 0 and 1. Okay. Okay. So, let us first say that the desired closed loop poles are at mu 1, mu 2 and mu 3. Okay. So, my characteristic equation, the desired one, would be like this. So, let us just write this down as say s cube, and let us denote the coefficient in terms of some alpha. So, this is like alpha 1 s square, alpha 2 times s plus alpha 3 is 0. So, this is the desired in such a way that mu 1, mu 2, mu 3 and in turn alpha 1, alpha 2, alpha 3 are known. Okay. Now, so this system is completely controllable. Okay. So, just because it is just in the controllable canonical form. Now, I say I want to appropriately place the poles of the closed loop system at mu 1, mu 2 and mu 3. So, what is the control law B is minus, say this will be K 1, K 2, K 3, x 1, x 2, x 3 that will achieve this configuration the closed loop. So, the unknowns here are K 1, K 2 and K 3. Okay. So, what is the characteristic equation, right? The characteristic equation is S I minus A plus B k. So, this would simply be S I minus, okay, what is A? 0, 1, 0, 0, 0, 1 minus A3 minus A2 minus A1 plus 0, 0, 1 say with some K1, K2, K3, and this minus will show up here. Okay. So, if I just write this down, I will get the following S I, okay, I will just write it completely in the matrix form. So, this matrix would be like this. I have a S here. So, this is the entire, okay, A, okay, actually this should actually be plus, because I am looking at Si minus A plus Bk. So, this minus and minus will cancel out. Okay, so, I have S, I have a -1, a 0, S and a 0. Here I will have A3 plus K3, A2 plus K2 and S plus A1 plus K1 equal to 0. Or in other words, this means that the characteristic equation now is S cube plus A1 plus K1 S square plus A2 plus K2 times S plus A3 plus K3 is 0. Now, I want to compare this with this, which essentially means that A1 plus K1 is alpha 1, or in other words, the unknown K1 can be determined as alpha 1 minus A1. This, the A1 is known to us, alpha 1 is also known to us. A1 is from the given system matrix, alpha 1 comes as a result of the desired closed loop poles. Similarly, then I can write K2 is 2 minus A2, K3 is alpha 3 minus A3. Okay. And you can just generalize this. If you have a system which is n by n, this generally Kn would be alpha n minus An. Okay. So, we will just write this down little formally now. Okay. Okay. So, I have the characteristic polynomial of this form, and if the system is not already in the controllable canonical form, I will use the transformation, right, the same thing, P inverse AP, or in this case I call it T, it will be T inverse AT, where I compute the transformation T in the following way. T is M times W, where M and W are computed. M is just the controllable, the controllability matrix, W comes from the entries of the A matrix in the following way. I will not tell you how to do this, but these are like very standard texts. So, once you have them in the controllable canonical form, then K's are simply computed this way, right, alphas, and you can just compute. So, alphas are known to us, A's are unknown to us, so I can directly compute what is the K matrix. So, what we have seen in this edition is the definition of controllability to check if the system is completely controllable or not, and if the system is completely controllable, how do I exactly do the control law. So, the only control technique which we have learnt here is what is called as the pole placement. There are other formulas typically called the Ackermann's formula. I will skip through those details, but what is important here is to know the concept, and once you know the concept, even the Ackermann's formula is kind of quite easy to derive. And you could also do the descent directly by MATLAB, but before you do, ask MATLAB to compute the gain matrix, the K matrix for you. It's very advantageous for you to know what is the procedure to compute the gain K, right. Okay. So, in the next lecture we will see about what to do if the system is not controllable, is there any hope, and also to learn the concept of observability, because so far we have been using things which says that the controller is of the form u equal to minus kx. Who tells us what the x is? Is it really trivial? If x is not known to us completely, say there are n states, I can only measure 2 states out of those n. Is there any hope? So, these are the 2 things which we will quickly run through in the next lecture. Thank you.